Howdy, howdy, this is Mr. Potter. In today's video, we're going to be talking about inverse functions. So I want to actually start by talking about what we know about regular functions. Keep in mind that f of x is a function that transitions values from the domain to the range. So if I have something like f of x equals x cubed, if I do f of 2, I know that's going to be 2 cubed, which is 8. So in other words, the element in my domain is 2, the element in my range is 8, and this is the point that we traditionally map when we graph a function. So I'm looking for every unique value in D maps to a value in R. So everything that's in my domain is going to map to a value in my range. Every x value here is going to give me one unique number in my range. Keep in mind that we're allowed to repeat numbers in our range. We saw that a lot when we were talking about a function like x squared. Because I could take g of 3, which is going to give me 9. I can also say g of negative 3, and that gives me a positive 9 as well. But keep in mind that g of 3 always gives me 9. No matter how many times I put a 3 in here, I'm always going to get a 9 out. That's what happens when we have a function. Every domain value, every unique domain value is going to map to only one range value. So when we're talking about an inverse function, we would say something like f negative 1 of x is an inverse function. Now, one thing you have to be careful of, this is not 1 over f of x. A lot of people think this negative 1 means you're taking the reciprocal, and that's not true. When we're talking about functions, the negative 1 represents an inverse. So f negative 1 of x is an inverse function. So this is a function that maps elements in the range of f to elements in the domain of f. In other words, I'm going to get numbers, I'm going to be starting off here and getting numbers here. In other words, f inverse, well, if I'm doing f inverse, that means I have to start off with a range number like 8. And I'm basically saying what cubed gives me 8. In this case, 2 cubed gives me 8. The problem is that if I try and talk about g inverse of 9, that actually causes a problem because I don't know. Am I looking for a positive 3 or am I looking for a negative 3? And so that really does mean that domain and range, these concepts that we've kind of glossed over in these previous videos, is really, really important. So I want to talk about now, how do we show that g is an inverse of f? So if I want to show that one function is an inverse of another function, so g is an inverse of f, if f of g of x gives me x, and g of f of x is equal to x on some domain. Now I'm going to talk about what this means in a later example, but I want to start by showing that g, which is equal to 2 over x plus 3, is an inverse of y equals 2 over x minus 3. So in other words, I want to prove that this is an inverse of this, which means everywhere that I see x, I want to replace x with this function. I want to find g of f of x. So I'm going to have 2 over my f of x plus 3. And my question is, this is g of f of x. Am I going to get an x out of this? Well, I know that when I divide by a fraction, I'm really multiplying by the reciprocal. So I'm going to have 2 times x minus 3 over 2 plus 3. And then I'm multiplying by 2, I'm dividing by 2. Those are multiplicative inverses. They eliminate each other. So I end up with x minus 3 plus 3, which is x. Well, that's good. That's one of these. But we do need to show the other one as well, f of g of x. So that means I'm going to take this function, which is really f of x, and everywhere I see an x, I'm going to replace it with g. So I'm going to say this is going to be 2 over this 2 over x plus 3 minus 3, because this whole thing is my x. Well, in my denominator, I have addition and subtraction. These are additive inverses. They will actually undo each other. So I've got 2 divided by 2 over x. And again, dividing by a fraction means we multiply by the reciprocal. And I'm dividing and multiplying by 2. They're inverses. They eliminate each other, which leaves us with x. So this is true. That means that f and g are inverse functions. Now, another thing that I need to stipulate here is on some domain. Keep in mind that I've got some problem points. One problem point I have is that x can't be equal to 0. The other problem point that I have is, of course, x can't be equal to 3. So in other words, my domain would go from negative infinity to 0, from 0 to 3, or from 3 to infinity. Any of those x's will work because they're not restricting our domain. There's nothing else in the process of doing this calculation that restricts our domain. And what's really important to note is that when we're talking about this, the domain of f is the range of f inverse. And the range of f is the domain of f inverse. So keep in mind that when I'm kind of going back and forth, because one function undoes the other function, the domains and ranges of each function really are exchanged. So I want to do another example. So I'm going to do another example here. F of x is x squared. G of x is the square root of x. Now, notice that these can't be inverses of each other for negative infinity to infinity, because negative infinity to 0 is not in the domain of g. Which means the only domain that I can really consider is from 0 to infinity. So we're going to have to consider x restricted to from 0 to infinity. That's going to have to be a restriction that I'm going to have to look at here, because that's a restriction that g has. Remember that we're trying to evaluate f of g of x. And I want to know, is this in fact equal to x? Well, if I take f of something, that something being the square root of x, I'm going to have the square root of x squared. We actually talked about this function last time. This is really the absolute value function. But because we have this restriction on our domain, x is restricted to going from 0 to infinity, this is in fact equal to x, because that's the piecewise definition that we talked about last time. It's x if x is greater than or equal to 0, and it's negative x if x is less than 0. So this way works out. We also need to check g of f of x. Well, that's going to be the square root of the quantity x squared. But keep in mind that square roots and squares, that's going to give me the absolute value of x as well. But again, for the very same reason that we have a restricted domain that is just x. So we can say that f and g are inverses on the domain from 0, including 0, to infinity. Now, let's try and do something very similar to that. Let's take a look at f of x equals 1 over x, and g of x equals 1 over x. And again, I need to ask myself, what restrictions do I have in my domain? Well, the only restriction I have is that x can't be equal to 0. So if I try and evaluate f of g of x, well, I'm taking the reciprocal of 1 over x, which is x. Well, that's good. If I take a look at g of f of x, I end up with the exact same thing. So f and g are inverses when x is not equal to 0. So this brings up some interesting points. We've been talking about x squared, 1 over x. Those are some of our parent functions. So what about our other parent functions? Well, let's analyze this. If I'm talking about f of x being x, well, then g of x equals x would be an inverse function as well. I have this nice symmetry. If I take x and substitute it into x, I get x. And similarly, if I take x and substitute it into x, I get x. If f of x is x cubed, then what undoes cubing something would be taking the cubed root. And because the domain of both of these functions are all reals, then we're good. This is going from negative infinity to infinity, as was the previous restriction. We talked about the reciprocal function. Well, what about 1 over x squared? Well, if I want to do 1 over x squared, I need to consider both undoing the reciprocal and undoing the square root. So, undoing the squaring, which means I need a square root. So I'm going to need something like 1 over radical x. But as soon as I do this, I'm introducing two restrictions to the domain. I can't be less than 0, and I can't be equal to 0. So my domain would have to be going the open interval from 0 to infinity. Similarly, if I were to take a look at f of x equals the absolute value of x, keep in mind that my domain is all real numbers, but my range is just going to be from 0 to infinity. So I need to consider what's going to happen. I need something that if I substitute a positive number in, I'm going to get only one set of numbers out. So g of x, my inverse, also ends up being the absolute value of x, but on that same restricted domain from 0 to infinity. That's still going to be a problem. Now there's two other functions that are going to be troublesome. One function is our constant function. And the idea is that if I'm talking about our constant function, then I'm talking about a horizontal line. We're actually going to talk about lines in our next chapter. If I want an inverse, I'm going to want some function that if I substitute a 1, gives me every possible number. Well, that kind of violates the whole rule of a function. So we're going to say, that's a problem. We're going to deal with it later. The other parent function that I want to talk about is our exponential function. And this I'm actually going to save as a riddle for later. Now, what's interesting here is that I need to remember that my domain can be all real numbers, but my range is going to be x strictly greater than 0. These are going to have to enter in to what I'm expecting for my inverse. So let's keep going. How do you find an inverse? So if y equals f of x is a one-to-one function. Now keep in mind, we've talked about one-to-one functions. Basically, one-to-one functions means that every y has a unique x that goes with it, just like every x had a unique y that went with it. If y equals f of x is a one-to-one function on a given domain, one can find the inverse on that range by solving for x equals f of y. In other words, I can work backwards using the properties of algebra to work backwards to try and find an inverse function. And I want to do a couple of examples of that. So I'm going to do an example, y equals 2 times the square root of x minus 3 plus 6. So what I want to do is I want to solve for this. So I have x equals 2 times the square root of y minus 3 plus 6. And I want to try and solve for y. And of course, the idea of solving something, I need to get rid of whatever term is farthest away from the y. In this case, it's that plus 6. So I'm going to subtract 6 from both sides. And this number in front of the square root is really a multiplication. I need to undo this multiplication. So I end up with x minus 6 over 2 equals the square root of y minus 3. And now I need to get rid of the square root. So I have the quantity x minus 6 over 2 squared equals y minus 3. And so I get y equals 3 plus the quantity x minus 6 over 2. And that's going to be my restricted domain. Now keep in mind that my domain has the restriction that x has to be greater than or equal to 3. That comes from this square root part. So I need to find out what my range of this function is going to be, because that's going to be the domain of my inverse function here. So if x is greater than or equal to 3, that means that I want to make sure that y minus 6 over 2 squared plus 3 is greater than or equal to 3. And so if I want this to be true, I need to make sure that, well, if I solve this, I end up with y minus 6 over 2 squared is greater than or equal to 0 by subtracting 3 from both sides. Then I'm going to unsquare both sides, take the square root, so I get y minus 6 over 2 is strictly greater than 0. So y minus 6 has to be strictly greater than 0. And so y is going to have to be greater than or equal to 6. So this is my range of my original function. Notice that if I substitute 0 into this function, I'm going to get a 6 out of it. Any bigger number than 0 is going to give me something bigger than this. As a matter of fact, 3 is the smallest number I could put in here. So that means that the domain of f inverse is x has to be greater than or equal to 6. So let's try another example of this. Let's say that I've got y equals 3 over x minus 5 plus 2. So if I try and solve this, remember the idea is that I want to find out what happens when I exchange x and y. First thing I'm going to do is subtract 2 from both sides. I can make anything a fraction by putting it over 1. I can cross multiply to get rid of the fraction part. So I have x minus 2 times y minus 5 equals 3. And so y minus 5 equals 3 over x minus 2. And so I get y equals 3 over x minus 2 plus 5. Now keep in mind that this is my inverse function here. Notice that the domain of f is that x can't be equal to 5. So the thing is, if I don't want x to be equal to 5, that means that I don't want this to be equal to 5. Well, that only causes a problem when x equals 2. Substituting x equals 5 in here gives me a problem, but I want to know what happens when y equals 5. Well, if I take a look at y equals 5, this fraction is never going to be equal to 0. I can't divide a number by an expression and end up with something equal to 0. But the only restriction I have is that x minus 2 can't be 0. So I have this restriction that basically says that f inverse of x equals 3 over x minus 2 plus 5 when x is not equal to 2. Last thing I want to talk about is a line of symmetry. When I take a look at a lot of these functions, I'm going to be noticing that I'm going to have some type of graph, like a parabola. And we noticed that we said that our inverse function for this parabola was a square root curve. And of course, we said that was only true if x was greater than 0. And one of the things that we notice is that we have a line of symmetry that passes through the origin, where basically all the points that were below the line of symmetry, these yellow points, end up reflected above the line of symmetry. And all the points that are above the line of symmetry end up getting reflected below the line of symmetry. So whenever we have a function f of x and the inverse, f inverse of x, they're always going to have a line of symmetry. And that line of symmetry is always going to be based on the line y equals x. Now keep in mind, we just talked about how substituting y and x for each other, in other words, having them trade places, allows me to find the inverse. And I mentioned earlier that we were going to be coming back to a riddle. So if I were to take a look at y equals 2 to the x, well, I know what the exponential function looks like. I know that it starts off really close to 0, goes through the point 0, 1, and then increases exponentially. And from today's lesson, I know that I'm supposed to have a line of symmetry, which means I know what the graph of my inverse should look like, even if I don't know an algebraic expression for it. I know it should go through the similar points. This point here is the point 0, 1, and if I exchange x and y, I get the point 1, 0. I know that it should go towards x equals negative infinity, so this should go towards y equals negative infinity. And this goes exponentially up and away from my line of symmetry, so this should go exponentially away from my line of symmetry. And so if this is f of x, then I know that f inverse of x should have this appearance, even though I don't necessarily know what that function is called yet. Once again, this is Mr. Potter. Thank you for watching. Have a great day.